If you haven't already figured it out, a lot of the questions in the exams are identical to these guys. But don't get complacent, because I might just get sneaky and change the wording around to make the answer different. Okay, so when you study these questions, be sure you understand why the answer. Then you'll be able to figure out any curveballs I throw at you. Okay, just a word of warning. All right, number one. In which of the following groupings are the three terms closely related? Okay. So we got these choices. And we have, let's just take them one at a time. Kinetic energy, energy of motion, cohesive forces. All right. Kinetic energy and energy of motion are virtually synonymous. All right. How about cohesive? Does that fit? Remember the difference, cohesive and adhesive forces. Cohesive holds together, disruptive, excuse me. Cohesive and disruptive. Kinetic energy is associated with disruptive forces, so A can't be it. Okay. Potential energy, energy of attraction, disruptive forces. Right? The first two are similar. The last one is wrong. Actually, the disruptive forces belongs with A. Everybody got that? Okay. Kinetic energy, electrostatic interactions, and disruptive forces. All right, kinetic energy and disruptive forces go together, but electrostatic attractions shouldn't be there. Electrostatic is a cohesive force. Potential energy, electrostatic interactions, and cohesive forces, those all go together. Okay, so D is the answer. How about two? The phrases particles close together and held in fixed positions and completely fills the container apply respectively to. Okay, so we've got two phases here that are together in the answers. The first one is described by particles close together and held in fixed positions. All right, what does that bring to mind? Yeah, it's a solid. All right. So if we look down at our answers, actually we can stop there. B's the only one that has solid first. We can check the second one just to be sure. Like gases completely fills the container. That's a gas. Right? So B is the best one. I think 3 is also highlighted. How many times larger in size is the atmosphere pressure unit than the millimeter mercury pressure unit? 1 atmosphere equals what? 760 millimeters of mercury. Right? Early on in the semester, I told you when you have an equivalence and the unit, let's do it this way. The number gets bigger, the unit has to get smaller. If they're equivalent. Right? So if the number gets bigger, the unit has to be smaller. By how much? 760 to 1. So that's why the answer is C. The ratio there is 760 to 1. All right. Let's make some room. Indicate what the missing words are in the following statement of Charles' law. Yeah. Remember 4 terms, 4 variables that completely describe a gas. Pressure, volume, temperature, and amount, moles. Okay, so Charles' law. At constant pressure, the volume of a gas sample is blank proportional to its temperature. At constant pressure, okay, I left one out. What else has to be constant? Moles, the amount of gas. So the volume of a gas sample is what? Directly or inversely proportional to its temperature. It's directly proportional. Remember, V divided by T is a constant. And whenever you have a quotient equal to a constant, those variables must be directly proportional. One goes up, the other one has to go up. But what else do we have to do with the temperature? We can't have any negative numbers in temperature. If you have negative numbers, then all bets are off, right? If you go negative with the temperature, then K is negative. Hiccup. All right, so the temperature has to be in Kelvin. If you start with Celsius, it goes to Kelvin because all you have to do is add 273 to Celsius and you got Kelvin. Plus, you have no negatives. Can't have negatives. So, directly proportional and Kelvin temperature. Answer is 4. All right. Let's see, 5. The correct form of the equation for the ideal gas law is, we normally see it this way. Pressure times volume equals moles times the gas constant times temperature. And in this case, it's A. But we could rearrange it, couldn't we? And we could arrange it to solve for anything we want. We could say solve for the number of moles, which is commonly, many of the problems that we've solved have been solving for moles. And if you do that, then moles becomes PV over RT. All right, number 6. What's the volume in liters occupied by 2.12 moles of nitrogen gas at 0.745 atmosphere pressure and a temperature of 55? Okay, when we're talking about gases and solving gas problems, we look at 2 possibilities, either a before and after or a state. What is it right now? Or if it gives you, say, 2 temperatures and two amounts of moles before and after, and it asks you what the pressure is if you start with this pressure and you end what pressure. Then you can use the combined gas law. But if you're only given single values for each one of those, P, V, T, and N, and one of them is missing, of course, then you have to go to your state solution, which is the ideal gas equation. And that looks like what we've got here. We've only got values, single values for each one. And I customarily do, right, if you have PV equals nRT, I set it up like, well, let's see, P here. PV, N, and T. Right. And then I extract information from the problem. Remember, if I haven't said it before, word problems are designed to confuse. They're trying to test to see if you really understand the concepts so that you can extract information from the problem and solve it. So they're not really clear. In fact, sometimes they have information you don't even need. So it's a good idea to extract the information out of it. To solve the problem, we're looking for volume. Right? That's the unknown. If we have 2.12 moles, and does it really matter that it's nitrogen gas? No. Gas is a gas is a gas. 0.75 atmospheres, 745. Okay, so we're good so far. Why am I writing the units in here? Because this is 0.08206 liter atmospheres per mole K. So when you're solving a state function like this, you need to match the units. Right? Atmospheres, moles, that's good. How about temperature? 55 degrees C. Can't go with that. We got to change that one. All right, so that'd be 8, 12, 328 K. Okay. Now that we have all our information up here, it's simple just to solve that equation for volume. nRT over P. Now we've done all the thinking. The rest is just number crunching. Plug the numbers in, crunch the values, and you get volume in what units? You get volume in liters. Okay. And that's our choice. Our choice is in liters. So I'm not going to go through all that. If you do the problem right, you should end up with 76.6 liters as your answer. All right, number 7. Partial pressure of helium in a gaseous mixture of helium and nitrogen trifluoride is, all right, so this is a generalized statement. We've got helium gas and nitrogen trifluoride gas together in a mixture. So the partial pressure of helium is what? Well, it's the pressure that helium would exert if it were all by itself. And none of that were there. Right? Each one exerts its own pressure. Right? Remember the kinetic molecular theory? These guys are bouncing around inside that container, and they're striking the walls. Of course, they're striking the detector. Right? Put the gauge on it. And the strikes that are due to helium contribute to its pressure. If there's more helium than there is this one, then it's going to have a higher pressure because they're all at the same temperature. And temperature is a measure of the average kinetic energy of all the molecules. So they're going to average a force of a certain amount. And if you have more of these, then the pressure is going to be higher for that one than it is for this one. So which one of these statements satisfies that? Let's see. The pressure that the helium would exert in the absence of nitrogen trifluoride. That looks pretty good to me. Right? It's like test-taking technique. Go down A through B, C, D. Once you find your answer, you can stop. Right? As long as you know what the answer is. Right? If you're confused, then you're probably going to read through all of them and do the X out, and try to work your way down to a choice between one or two, and then guess. I know how to take multiple choice tests. But if you know the answer, then we're done. It's A. All right, number 9. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? Not a factor. What is the vapor pressure of a liquid? Right. Our example was an Erlenmeyer flask, right? And you have a liquid in the bottom. Right? And we put a stopper in it. And in the beginning, the molecules in here are only going in one direction. They're going into the vapor phase. Okay. Once you get some of them up here in the vapor phase, then you get enough of them, and you gradually get a return. Right? They're going both ways. And when you reach a balance, the rate of evaporation is equal to the rate of condensation, then the pressure stabilizes. Okay? So what determines the vapor pressure? Well, first and foremost is, what's the molecule? What are the attractive forces between the molecules in the liquid that are holding it in a liquid? If they're very weak, then it's going to go like gangbusters this way before it gets enough to return. So low intermolecular forces between the molecules will give you a higher pressure. And I think the example we used was ethanol versus diethyl ether or dimethyl ether. Okay, same formula, different structure. Ethanol has a stronger intermolecular force and ether doesn't. So ether is going to have a huge vapor pressure. Ethanol will have less. So that's one of the factors. What's another factor? Well, how do these things leave the surface? They got to have energy, right? They got to go, in order to evaporate, the molecule has to have enough energy to leave, to break the bonds with its neighbors. So temperature is in effect there also. So let's see. Which of the following is not a factor? Key word there is not. Temperature of the liquid. No, that's a factor. The strength of the attractive forces between the molecules. That's a factor. C, the size of the container for the liquid. That's not a factor. With one caveat. You got enough liquid to establish the vapor pressure. If you just put a few drops in there and you have a big container, all of it's going to evaporate and you're not going to have any liquid left, right? So we have to make allowances. But assuming you've got liquid and vapor both, the size of the container doesn't matter. The type of the forces between molecules within the liquid, that's another way of saying B. So C is the one that is not a factor. The size of the container doesn't matter. How about 10? A liquid is placed in a closed container. Equilibrium is reached when? So we're still talking about that vapor pressure. All of the liquid evaporates. You can't have equilibrium when there's no liquid, right? Okay, so it can't be that one. When the rate of condensation equals the rate of evaporation. That's it. When those two rates are equal, you have equilibrium. Oh, you need to sign in. Sorry. There you go. That's all right. So the answer is B. Number 11. Well, so far, we're doing all of them. Liquids will boil at lower temperatures at higher elevations because we're still in the neighborhood of vapor pressure, except that now we have infinite space above our liquid. So when will a liquid boil? When it boils, what are we saying? We're saying that at that temperature, the vapor pressure of the liquid is equal to the pressure bearing down on it. So at sea level, that average pressure would be 1 atmosphere, right? So the temperature at which that liquid boils would equal that 1 atmosphere pressure. For water, it's 100 degrees Celsius. Right? For ethanol, it's in the neighborhood of 73 or 4. As you increase your elevation, you have less atmosphere above you, so lower pressure. So as you go up, say, to the top of Mount Everest, right, the pressure is very low, and water boils at a much lower temperature because it doesn't have to overcome 1 atmosphere. It's a lot less than 1 atmosphere. So having said that, liquids will boil at lower temperatures at higher elevations because the intermolecular attractions are weaker. No, they're the same. Right? That's characteristic of the molecule. Atmospheric pressure increases. I think it's the other way around, isn't it? It's harder to transfer heat to the liquid. No, I don't see that as a problem. Vapor pressure at which boiling occurs is lower. That's it. The vapor pressure is lower for the boiling point. Now, number 12. All right. Which of the following statements about intermolecular forces is incorrect? All right. They must be overcome in order for molecules to escape from the liquid state into the vapor state. Right? Keyword there is incorrect. Since if you look at all your answers, you don't have any of those squirrely ones like none of the above or 2 of the above, that type of thing. So we need to look at each one and see which one's wrong. Right? A is correct. How about B? They're much weaker than intramolecular forces. Is that true? Intermolecular forces between molecules. Intramolecular forces, they hold the molecule together. Right? So that's true. Why, as a practical matter, why would we say that's true? Intermolecular forces are weaker than the intramolecular. What would happen if it was the other way around? If intermolecular forces were stronger than the forces holding molecules together, it would rip them apart. Right? The external forces would be so strong, they just pull the molecule apart. And if you made a molecule, it wouldn't be there for very long. Right? So it has to be intramolecular forces are stronger. So B is correct. They are electrostatic in origin. Yeah. Right. You get what types of electrostatic attractions can you get? You could have ions, right? You could have ions attracting one another. You could have partial charges or polar molecules attracting one another. Right? They're slightly positive on one side, slightly negative on the other. So they attract one another like water molecules. Right? Those are electrostatics. How about neutral molecules? Right? Like methane or ethane or any of the hydrocarbons, octane in your gas tank. What's holding them together? London dispersion forces. That's still electrostatic. I mean, it only happens for a split second, but it's still electrostatic. They're all electrostatic in origin. So by process of elimination, D must be the bad one. They occur within molecules rather than between. Right? That's wrong. Inter means between. Anybody out there? I'm talking about you guys. You can't all be sick. I guess you could all be asleep. It's possible. Or sleepwalking. In which of the following liquids would London forces be the predominant intermolecular force? All right. In order for London to be a predominant force, remember, London dispersion forces are always there. Always. No matter what else the molecule is doing, London dispersion forces are there. The question is, since they're so weak, are there other forces that are so strong that London dispersion forces don't matter? Right? So what we have to do is to answer this question, is to find the molecule that has no other forces that would overwhelm the London dispersion forces. Right? If we're looking at HCN, right, that's a polar molecule. Right? Because nitrogen, for one, is more electronegative than carbon. So it's going to have a dipole in that direction. And so that would be too strong for London dispersion. Can't work. H2S. Right? It's like water. It's a bent molecule, and sulfur is more electronegative, so it's going to have it's a polar molecule that way. Iodine, fluoride, it's the same way. Fluorine is more electronegative, it's going to be polar. So the only one left is nitrogen, dinitrogen. Right? It's nonpolar. Why? Because it's got two nitrogens together. They're equally pulling on the electron density. So they're going to be symmetrical. There's no polarity there. That's the one where London dispersion forces would be a significant contributor to intermolecular attractions. Now, how do we know London dispersion forces are really there? Because if they weren't, we could compress nitrogen down to nothing and it would still be a gas. But if you cool it and compress it far enough, below 195 degrees Celsius, minus 195 degrees Celsius, it turns to a liquid. The only way a gas can turn to a liquid if the molecules are attracting one another. So we know those forces are there. We just named them after London, not the city, the person. And not Jack London, not Call the Wild. That's a different London, a scientist. Do they still read classics in school? Good. I'm glad to hear that. I mean, I don't know if Jack London's considered, Call the Wild's considered a classic, but you know, things like I don't know, Shakespeare's plays. Right? Do they do those anymore? Did a couple? Good. My all-time favorite is Hamlet. The movie too. The Laurence Olivier version of Hamlet, that's black and white. But you talk about a ghost story. I mean, the very first scene will scare you. Yeah. When he meets his father's ghost. You ought to look that one up. I mean, it's got a good story to work with to start with. And then Laurence Olivier is a master. So good combination. 15. That had absolutely nothing to do with chemistry. Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 atmospheres to 1 atmosphere? Okay, now what do we have? We got a gas law solution that requires what? Before and after. Because we have 2 pressures and only 1 volume. Okay, so whose law is that? Pressure volume. You just did an experiment with it. Yeah, Boyle's. So P1 V1 equals P2 V2. We have to decide which one's which. That's the trick with these equations. If you put your numbers in the wrong place, you're going to get the wrong answer. So a new volume of 3 liters. A new volume of 3 liters. So this is the new volume here, 3 liters. The old volume was what? We don't know. Okay, so that's unknown. The first pressure, if the pressure is decreased from 3 atmospheres to 1 atmosphere. Okay, now we can solve for this one. V1 equals P2 V2 over P1. Right? So we did 1 atmosphere. Second volume is 3. And the first pressure is 3. Right? 3's canceled. 1 liter. V1 is 1 liter. So which one is that? A, 1 liter of helium is the answer. Okay. All right. The only reason I did that one was it was quick. 16. All right. Which of the following is a correct equation for the combined gas law? All right. How do we write the combined gas law? Well, I added a term in there. All right. When I wrote the combined gas law, I said P1 V1 over N1 T1 equals P2 V2 over N2 T2. But their solution has no moles in it. Right. So what we should do then to satisfy that problem is just throw the moles out. And then we've got P2, V2, and T2 possibilities. P2, V2, and T2. So if we solve this equation for P2, right, it's going to be P2 on one side with P1, V1, T2, right, comes over here, and then T1 matches up with V2. Right. Is that the way they have it written? No. They got T1 on top and T2 on the bottom. So A is wrong. B, C. That's it. A is wrong. Okay, solve for V2. V2 here. All right, so P1, V1 times T2. Yeah, P1, V1, T2. And then keep this one and put this one over here. T1, P2. How about that one? V1, P2, T2. Nope. Wrong again. All right. And T2. Let's solve for T2. All right, T2 would have to come over here. And then T1, P2, V2 is over here. And then P1, V1 goes over here by itself. Okay. So T2 and P1. Oh, V2 on top. They've got V1 on top. All right, so none of them are right. Right? No correct answer is E. That's the one. So what could I do with this problem? I could change it so one of them was the right answer. Okay. Just a cautionary statement. Don't just go in and memorize answers because it might be a fatal mistake. All right, 17. Okay, we're doing good. When the vapor pressure of a liquid equals atmospheric pressure, the temperature of the liquid equals the boiling point of the liquid, doesn't it? Except we have two possibilities, right? B is the boiling point of the liquid. C is the normal boiling point of the liquid. When we're measuring that's not a good question. If we just take it at its face value, this is the boiling point of the liquid. Atmospheric pressure. Atmospheric pressure could be anything, right? At sea level, it could be 1 atmosphere. Here it could be 0.9, what was it, 0.98 something when we did our experiment. Or in Beckley, it could be 0.97 or 0.965. Right, so that's a bad question. If you want the answer C, the normal boiling point of the liquid, you have to say the vapor pressure of the liquid equals 1 atmosphere pressure. That's the normal boiling point. What normal means is the boiling point is normalized to 1 atmosphere pressure. So technically speaking, the answer instead of C should be D, more than one correct response, B or C. Or B could be the right answer, right? So if I let that one slip through, you can, and I count it wrong, you can call me on it, okay? Because you have other options that are technically correct, okay? All right. 18. Intermolecular forces differ from intramolecular forces in that, let's see, they occur only in liquids. No, they occur in any phase. They're different. Intermolecular, right, between molecules versus within molecules. They're much stronger. Intermolecular forces are not much stronger. Right? So A and B are both false. They occur only when hydrogen atoms are present. That's kind of stupid. So there's not a correct response. None of those are correct. All right. As long as you see why, then we've accomplished our mission. 19. In which of the following pairs of molecules would the first listed member of the pair have a higher boiling point than the second listed member of the pair? All right, so what would change the boiling point of a liquid? The strength of the forces. Right? The strength of the forces between the molecules, because everything else is equal, except for the temperature. We have to assume that the atmospheric pressure that's bearing down on either one is the same. They both start off as liquids, right? Some of them we know are gases to begin with, so they would have a very low boiling point. But the difference in the boiling points is relative to the forces that are holding them together. So the first one needs to be a higher boiling point than the second one. All right. Let's see, HF versus HBr. Let me just write them all up here so we can talk about them. F2 and Cl2 and O2 and NO. Right? And then D is more than one and E is no correct answer. So which one of these has the higher boiling point? Well, look at what you've got. What kind of forces are we talking about here? If you got HF and HBr, the electronegativity of Br is greater than hydrogen, so we're going to have a dipole moment that direction, right? Same for this one. But which one's stronger? This one. Because fluorine has a higher electronegativity than bromine, right? So we found one right answer. The first one is stronger, has a higher boiling point because the intermolecular forces are much stronger. That means we have to heat it higher to overcome those forces. Okay, so A is good. How about B? Well, what forces do we have here? Right, you got fluorine, difluorine, and dichlorine. We don't have polarity here to deal with. What we have is London dispersion forces. And London dispersion forces are larger for larger molecules. Right? Chlorine is below fluorine in its group. Right? So these are larger than those. This one would have the higher boiling point because it's bigger. Okay, so that one's out. How about these two? Well, this one's nonpolar. And this one, nitrogen, oxygen, let's see. It's probably like that. I'm just guessing. Anyway, we've got a difference in electronegativities between nitrogen and oxygen. Right? Oxygen's higher, so it's going to be slightly polar that way. This is nonpolar, so this one's going to be the stronger one. Right? So we found our answer. A would have the higher boiling point because the intermolecular forces are stronger for the first one than they are for the second one. Oh, goody. Twenty. This is one of them. Remember these questions. Which one of these three, 1, 2, or 3, is true? Right. So the first one, sublimation and deposition are opposite changes of state. Is that true? Yeah. Sublimation is going from solid to gas, correct? Think dry ice. Deposition goes the other direction. Gas to solid. So number 1 is true. How about 2? A pressure of 1 atmosphere is greater in magnitude than a pressure of 720 torr. Is that true? How many torr is 1 atmosphere? That was our first question. 760. 760 is greater than 720, right? That one's true. How about 3? The boiling point of a liquid can be increased by heating the liquid to a higher temperature. I don't think so. Doesn't depend on the temperature. The temperature is the boiling point. Boiling point depends on 2 things: intermolecular forces and external atmospheric pressure. So 3 is false. 1 and 2, there are only 2 correct answers. That's B. 21. Let's see. 1. Associated with Charles' law is the concept that if the temperature of a gas increases, the volume of the gas increases. True? Volume and temperature directly proportional. Yep, that's true for Charles' law. Liquids show little change in volume with changes in temperature. That's technically true. Liquids don't expand much. The key word there is little. They do change, but they change very little in volume with the change in temperature. So 2 is also true. Dipole-dipole interactions are examples of intramolecular forces. We'll throw that one out now. Those are intermolecular forces. Hydrogen bonds are an example of intermolecular forces. That's true. But the dipole-dipoles are also intermolecular. All right, so 3 is false. So B is your answer. 2 of the above. 22. Both dipole-dipole interactions and hydrogen bonds are stronger than most single covalent bonds. True? False? False. You're comparing intermolecular forces with intramolecular. Intras are always stronger than intermolecular forces. So 1 is false. 2, the value of the ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. Yeah, that's true. Right? A gas is a gas is a gas. Both condensation and freezing are endothermic changes of state. Let's see. Condensation, we're going from gas to liquid for the first one. And the second one, freezing. We're going from liquid to solid, right? are those endothermic changes. When you go from a gas to a liquid, you got to give up energy, don't you? Right? So that's exothermic. Liquid to solid, exothermic. So 3 is false also. Only 2 is right. Only 1 is correct. C is the answer. Let's see. We get another one, 25. Water's boiling point is much lower than expected. Is that true? Water's boiling point is lower than expected. No, it's the other way around. Water's boiling point is much, much higher than expected. Right? So throw 1 out just on that beginning statement. Doesn't matter what the because is. It's false on its face. 2, in the gaseous state, disruptive forces and cohesive forces are about the same magnitude. Is that true? Disruptive is much, much higher. Right? 2 is false. How about 3? As liquid surface area increases, the rate of evaporation of liquid increases because molecules encounter less external pressure. The first part of the statement is true, but the second part of the statement is wrong. It's not because molecules encounter less external pressure. It's because there's more surface area, right? The rate is related to the surface area, right? So 3 is false also. None of those are true. Okay, D is the answer. 26. Get back to a normal one now. Okay. For each of the physical state characterizations, select from the response list the physical state or states to which the characterization applies indefinite shape. An indefinite shape. Well, solid is a definite shape, right? Liquid is acquires the shape of the container, and it can be an open container. Gas acquires the shape of the container, but it has to be completely enclosed. So liquids and gases would satisfy indefinite shape. Let's see, both liquids and solid state? No. D, gas and liquid states. D would satisfy that statement. All right. 28. For each of the physical, let's see, states. Oh, okay. We're going to characterize physical states by this statement. Potential energy dominates over kinetic energy. So potential energy, we're saying, is the cohesive force. If it dominates, then we've got over the kinetic energy or the disruptive force, then we have a solid state. What if we have a liquid? They're in balance, roughly. Disruptive versus cohesive. And if disruptive is dominant, then we have a gas. So B, solid state satisfies that condition. All right, 29. Particles are relatively close together. We know that's true for a solid. How about a liquid? Are they still relatively close together? Yeah. They've got enough energy so they can slide past one another. With a solid, they can't. They're locked in place. So both solids and liquids, C, they satisfy that condition. About 30. Consider the mathematical expression for gas laws listed. Select the correct name for the law from the response list. All right. Yeah. You could do that one in your sleep. How about 31? Okay. 31. Consider the mathematical expression. Oh, okay. Yeah, Charles' law, volume and temperature. Oh, okay. 32 is the same way, only it's solved for a different way. It's still Charles' law. Let's see, let's go down to 34. Somebody cooking something? Or is that our heaters giving off some smell? Oh, I see. Gotta feed the bureaucrats, right? 34. Considering change of state description, select the name of the change of state for when energy is absorbed. So when energy is absorbed, we go from either solid to liquid, liquid to gas, or solid to gas. We got to put energy in to get those molecules apart. So sublimation, yeah, sublimation would work. You go from a solid to a gas. That works. Condensation is the other way around. Condensation goes from a gas to a liquid, and it gives up energy. And this one absorbs energy. Well, we found our answer, right? There are no squirrely ones in there, so time to move on. 36. Characterize the effect that changes will have on the vapor pressure and boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees at constant pressure. So we're talking about vapor pressure and boiling point. All right, we're looking at vapor pressure and boiling point. And what are we doing to it? Decrease the temperature of the liquid by 20 degrees. Okay, pressure is constant. And temperature, change in temperature is a negative 20 degrees C. We're decreasing the temperature by 20 degrees. Okay. All right, so at constant pressure, which one of these is true? All right. What does change in temperature has an effect on what? It does have an effect on vapor pressure, doesn't it? How about boiling point? Well, the boiling point is a measure of temperature. So a change in temperature doesn't affect it at all, right? There's no effect on the boiling point when you increase the temperature, right? So this has no effect. And when we decrease, the vapor pressure should decrease because we're removing energy from those molecules and they can't escape from the surface to make the pressure. All right, so the one that satisfies that is B. Vapor pressure decreases, boiling point doesn't change. All right. Okay, 38. For the following intermolecular force descriptions, A through D, select the correct name from the response list. Permanent electrostatic interactions between polar molecules in which no hydrogen is present. That's a dipole-dipole. You get two polar molecules with their own dipoles. They're not fully charged, but they do have an uneven distribution of charge. That's dipole-dipole. If they had said where hydrogen is present, you would say hydrogen bond. If they had said temporary electrostatic interaction between nonpolar molecules. That's London forces. Okay. And a covalent bond is not intermolecular anyway. So just throw that one out. All right. Let's get 40 and 41 together. A solution may contain what? Okay, it looks like solvent and solute descriptions. All right, a solution can only have one solvent. And it can have many solutes. So which one's one solvent, many solvents? Well, that's A. Okay. That was easy. .41. Which of the following statements concerning a saturated solution is incorrect? What is a saturated solution? Well, obviously it's a solution. It's a solution in which the solute is at maximum concentration. You can't put any more in there at that given temperature. And for gases at that pressure. We generally speak of saturated solutions in terms of liquids and solids or liquids and liquids. We generally don't discuss saturated solution with liquids and gases, although it can be, but we haven't presented it that way. All right, so undissolved solute must be present. That's incorrect. You don't have to have undissolved solute. You can have undissolved solute be present. Right? That's one way to know that your solution is saturated, but you don't have to. How would I make a saturated solution that had no solvent present? I mean, excuse me, no undissolved solute present. I described this in class. I distinctly remember. You make the saturated solution at a given temperature, and you have solid present in the bottom. You let it sit there long enough to come to equilibrium, and you have solid in the bottom, and you know that the solution then is saturated. And you filter it. You just filter out the solid. Now you've got a solution that's saturated with no solute, undissolved solute in the bottom. Okay. So A is the answer. 43. For which of the following types of ionic compounds are most examples insoluble in water? All right. You can use that. Let me check. Let me check to be sure it's present. Ooh, it's not there. Well, it's not in the key. Let's see. No. Oh, there it is. Okay. So the exam does have that chart. It also has the rules. No, it doesn't have the rules. It just has the chart. So if you look at that chart and you look at the nitrates and you follow the nitrates across, because the anions are on the left and the cations across the top. If you go to the nitrates and look across, they're all completely clear squares, right? Everything in that chart is soluble as a nitrate. So A is not it, right? Nitrates are all soluble. How about B? Sulfates. Most sulfates are soluble. But I should be consistent. This is sulfate. Most sulfates are soluble. Some of them are not. So B's not it. How about C? Hydroxides. hydroxides are nearly all insoluble. Which ones are soluble? The alkali metals, lithium hydroxide, sodium hydroxide, potassium hydroxide, they're all soluble because alkali metal combinations with anions are always soluble. Right. So hydroxides, most of them are not soluble, and most chlorides are soluble. There's some examples, right? Most notably, silver chloride is insoluble. All right, 45. We have to do some math here, I think. What is the molarity of a solution containing 16.7 grams of ammonia in 1.5 liter of solution? So this is the mass, and the volume is 1.5 liter. All right, so our answers are in molarity, which means what? Can't use grams. Got to use moles. Right, so you got to change grams to moles. Okay, so we need the molar mass of ammonia. Right. Nitrogen is 14.01 grams per mole. Hydrogen is 1.01 times 3, right? 3.03. So that's 1704. All right, so we divide that into 16.7. 17.04 divided, and I get 0.980 moles. Now we can do the calculation for molarity, moles per unit volume. 0.980 moles divided by 1.5 liters. And I get 0.653 molar. B is the answer. Okay. All right. That was simple enough. How about 46? If 145 milliliters of 2 molar potassium hydroxide is diluted to 1.15 liters, the resulting solution contains so many moles of KOH. All right. This can be misleading. Let's write what we've got up here. 145 milliliters of a concentration of KOH. Molarity of KOH is 2 molar. And it's diluted to 1.15 liters. So this is the initial volume, and this is the final volume. 1.15 liters. So the question is, how many moles of KOH does this contain? It contains the same moles you started with. Right? You start with moles over here, you end up with moles over here. Right? So you don't even need that. You know how much you started with, that molarity and that volume. But if we're going to use moles, this has to be in liters. So how many liters is 145 milliliters? Right? Milli means 1,000th of. So we go 1, 2, 3. So that many liters. And if the formula is moles per that, then moles equals molarity times volume, which is 2 molar times 0.145 liters. Okay, so that's about two point three something, 0.3 something, 0.29, 0.29 moles of KOH. Yep. Now, if we wanted to know the concentration of the final solution, then we take that molarity and divide it by this volume, and that would give us the molarity of the final solution. But that's not the question. The question is just want to know how many moles are being transferred. 47. We were given more information than we needed to answer the question. A colloidal dispersion differs from a suspension in that colloidal particles what? Do they tend to settle? No. Colloid is not a solution, but it's not a suspension either because the particles don't settle. Right? What keeps them up there? What keeps them from settling? Two words: kinetic energy. The kinetic energy of the dispersing medium impacting those dispersed medium particles keeps them suspended. So they have to be smaller than a certain size. If they were too big, then the impacts from the dispersing medium wouldn't be enough to keep them suspended. And there I'm convoluting two terms. It wouldn't be enough to keep them in the colloid. Okay, so A is wrong. B, are large enough to scatter light. Colloidal dispersions differ from a suspension. Well, that's true. Right? They're large enough to scatter light. Right? What effect is that? That's got a name. Tyndall. The Tyndall effect. That's how we know we have a solution or a colloid. If we got a solution, we can shine a light through it, and at right angles, you can't see the light beam through the solution. But if it's a colloid, you can shine a light beam through it, and you can see the beam travel through the solution, the colloid. Okay, so B was our answer. How about 48? Compared to pure water, a 1 molar sugar water solution will have a what? Now we're talking about vapor pressure, boiling point, freezing point. So vapor pressure, boiling point's next, yep, and freezing point. So if our solution is 1 molar sugar water, 1 molar sugar in water, what does that do to these various things? If you add a non-volatile solute to a pure solvent, you decrease its vapor pressure. Right? We're going to decrease the vapor pressure. How about the boiling point? You increase the boiling point. Right? That's one of the reasons we put antifreeze in our radiators. Right? They can run hotter than 100 degrees Celsius. And they typically do run hotter than that without boiling. Right? If you have one of these old cars that's not doing too well, right, and it loses its antifreeze, and you're stuck out there, and all you got is pure water. You pour pure water into your radiator. What's going to happen? Well, in a few miles, you're going to have to add more water because it's going to boil off. And the cap is set for, it's got a pressure sensitive thing on it. And the cap is going to blow off that excess steam rather than rupture your radiator. So you're going to stop every few miles and add more water. But if you got antifreeze in there, and typically it's 50-50, then you can run it now till Sunday and you're good. You increase the boiling point by adding a solute. How about the freezing point? What happens to the freezing point? Yeah, like ice cream, right? Right? Add salt to ice. You make salt water. It freezes at a lower temperature, and the temperature of your churn goes like that, so you can freeze your custard. So down, up, down. Which one satisfies that? Let's see. Lower the vapor pressure, A, C, or D. Increase the boiling point would be C. That's the only one that fits. And then lower the freezing point in that same. So C is the answer. Okay. See how I analyze the problem first, and then I look for the answer. All right, 49. What is the freezing point for a solution containing 1 mole of sodium chloride dissolved in 1 kilogram of water? All right, so if we've got 1 mole per 1 kilogram of solvent, what is that? That's 1 molal. Okay? All right. What's the freezing point for a solution? All right, this is in water. So the expression, freezing point, change in freezing point equals what? The freezing point constant for water times, let's see, what do we got? Sodium chloride. This is 1 molal sodium chloride. So we have a Van Hoff factor, I think it's Van Hoff, times the molality. So what's the factor for sodium chloride? Right, sodium chloride becomes sodium ions plus chloride ions in solution. So the factor is 2. Right, so we know that one is 2. Molality is 1. What's the K? Oh, it's not given. Okay. So I'd have to give you that one. I think it's 1.86. So it's 1.86 degrees C per molal. And so the molals cancel. It gives you degrees C. This is the change. Right? So the change in freezing point is 1.86 degrees C delta T. Well, if it's a freezing point change, what does that mean? That means the temperature decreased by that much. So the actual freezing point temperature is equal to minus 1.86 degrees C. Oh, excuse me. I forgot my I. What's 2 times 1.86? Well, 73, right? So the freezing point is minus 3.72 degrees C. There you go. You know what might be safer? This is the molality for the molecule or the formula. What's the molality for the ions? It's 2. So if you make that change here, say it's 2 moles of ions, then you have 2 molal of the ions, and you can drop this out. And then you're less likely to make that mistake that I just made. Okay. 50. Crenation of red blood cells occurs when cells are placed in what type of solution? What's crenation?
Cells shrink.
Yeah, they kind of shrivel up and get bumpy. Right. So if you put them in some type of solution, what do they have to do for the cell to go to that? Which way does the water move?
Just use it.
Right. Water goes out. So that means outside the solution has to be hypertonic.
Mm-hmm. We know all about that.
You know that one? Yeah.
Yeah.
You must have got it somewhere else.
Well, we're MLT students.
Yeah.
So we're learning about red blood cells.
Oh, you're in that right now.
Yeah.
Yeah.
Okay. It's fresh.
Yes.
Okay. So let's say if you have a patient, you want to start an IV with 20% sodium chloride solution. If you want to kill them, right? Okay. Don't do that. 51. Which of the following solutions is hypertonic with respect to blood? Hypertonic. It's more concentrated. Right? So what's isotonic? Sodium chloride. 0.9%. Okay, mass volume. That's isotonic. So anything greater than that would be hypertonic, wouldn't it? Well, this is isotonic sodium chloride. So it would be 1.8. Well, actually, no, that doesn't work because sodium and chlorine have different masses, right? So mass volume doesn't work. All right. See, this is more complicated than I thought it was. Hypertonic. Well, obviously, 0.5 and 0.7 are hypotonic. Right? That's easy. Oh, here's the solution, the easy solution. What's the other way? What's the other type of isotonic solution that MLTs, not EMTs carry?
Glucose.
Yeah, D5W. So, right, dextrose, which is essentially glucose, 5% by weight. So 5% glucose is isotonic. So 4.5 is hypotonic, 7.6 is hypertonic. That's it right there. D. There you go. Okay. I thought it was going to be difficult for a second, and then I realized we had two options for isotonic. All right, 52. Which of the following statements about solutions is correct? A solution is a homogeneous mixture. Yeah. That's true on its face. A is true. How about B? It's possible to have solutions in which both solute and solvent are solids. Yeah, that's true. Think brass. C, solutions readily separate into solute and solvent if left undisturbed for 24 hours. Solutions do not separate voluntarily. So more than one is correct. D is correct. 53. A crystal of solid sodium chloride is placed in an aqueous sodium chloride solution. It's observed that most, but not all, of the crystal dissolves. This means the original solution was unsaturated. Yeah. Mhm. So after some of it dissolves, it becomes saturated. But that wasn't the question. Unsaturated is the answer. Bit 4. Consider the following substances and their polarities. Okay, A is polar. B is polar. C is nonpolar. Do better than that. C. And D is nonpolar. All right. It is true that what? A is more soluble in C than B. A is more soluble in C than B. False. Like dissolves like, right? So A will be soluble in B, C will be soluble in D, but neither of the twain shall meet. C is more soluble in D than in A. That's true. B is true. We have to look at C because we have one of those more than one and none of the above. D is more soluble in B than in C. False. So B is the only answer. And all you need for that one is a rule of thumb. Like dissolves like. All right, 55. We're going on time. Okay, got about a half hour. In which of the following sets of ionic compounds are all members of the set insoluble in water? Okay, so what you may have to do is go look at your solubility chart. All right, I can tell you that A, silver chloride is not soluble. Lead chloride is not soluble. Ammonium chloride is soluble. So A doesn't have all members of the set are insoluble. Right, so A only has 2 that are insoluble. Right, it doesn't work. How about B? Copper carbonate, calcium carbonate, magnesium carbonate. Those are all insoluble. In fact, most carbonates are insoluble. Most carbonates are insoluble. Which carbonate is soluble? Any one of the alkali metals. Sodium carbonate, lithium carbonate, potassium carbonate, they're all soluble. But that list, they're all insoluble. Sulfates. Barium sulfate is insoluble. Iron 2 sulfate, lead sulfate. Iron 2 sulfate is soluble. All right, so C is not the answer. Has to be B. '61 and '62. Which of the following solutions has an osmolarity of 3? So we want 3 osmol. Right. So what are the possibilities here? If our solute does not dissociate, then this would be equal to not 3 mol, 3 molar. If it dissociates into 2, then it would be 1.5 molar. Right? If it's undissociated, if it's 2 products, how about if it's 3 products, it'll be 1 molar. Would produce 3 osmol. So what are our choices here? Let's see, 4 molar glucose would be 4 osmol because it does not dissociate. Um, 2 molar sodium chloride would be 4 osmol, right? 1 molar sodium phosphate would be what? 4 osmol. You get 3 sodiums and 1 phosphate. That's 4 particles per molecule. So none of the above are correct. Right? They're all wrong. '62. In which of the following pairings are the terms closely related? All right. Hemolysis. What's hemolysis? Right. It's the other direction from crenation. So you need a hypotonic solution, right? Right. So A is correct. Right. Makes it blow up. Water moves into the cell. Okay. How about B? Hypertonic, higher osmotic pressure than within the cells. Yeah, that's true. Right. B is true. How about C? Isotonic solution. No, C doesn't work. But more than one is correct. So D is the answer. All right, 63. Let's see which ones of these are true. Equal volumes of 2 solutions of the same molarity contain the same number of grams of solute. If they're the same molarity, they have the same number of moles. But if they're different compounds, they won't have the same mass. Right? So 1 is false. 2, hemolysis and crenation are opposite processes. Yes, that's true. 3, the solubility rule, like dissolves like, is not adequate for predicting the solubility of ionic compounds in water. Is not adequate. Well, that makes it false because it is adequate. Right? So only 1 is true. Oh, the answer is not there. Only one of the statements is true. That's C. Should be a C. Can I correct that? There we go. Let's save it for posterity. Okay, 65. Did I put the right one for that? Yeah, only one of the statements is true. Okay, 65. Addition of 40 milliliters of water to 10 milliliters of 8 molar sodium hydroxide will produce a 2 molar sodium hydroxide solution. All right, for this one, we need our dilution formula, right? M1B1 equals M2B2. So what's M1? Molarity 1 is 8 molar sodium hydroxide. Okay. Oh, let's do it like this. Right, because we have, it's not obvious how we're diluting this. 40 milliliters of water to 10 milliliters of 8 molar sodium hydroxide. So the initial volume here is 10 milliliters of 8 molar, right? So far, so good. Okay. We're going to add 40 milliliters of water. So if we add 40 milliliters to that, the final volume is 50 milliliters. Correct? Then we can do this. All right, so that's correct. B1 is 10. M2 is unknown, and V2 is 50. Okay, so M2 is 8 times 10 divided by 50. That's 80 divided by 50, or 8 divided by 5. So that's 1 point, see, 5 into, see, wait a minute, 536, 1.6 molar. Right, it says it should be 2 molar. No, 1 is false. Okay. Everybody see that? That goes too fast. Two. Henry's law is a pressure solubility relationship for gases and liquids. Yeah. Right. Increase the pressure, you get a higher concentration. And so 2 is true. 3. Boiling points are the basis for the solubility rule, like dissolved like. The boiling points, no, it's not the boiling point that's the basis. It's the polarity that's the basis. Now, the polarity may have an effect on boiling point, but the boiling point and like dissolves like are drawn from the same common characteristic, which is polarity of the molecules. Right? So we can't say that boiling point leads to 1. Boiling point is a consequence of the same thing as like dissolves like. All right, so really only 1 is true. Right? C. Only one of those statements is true. 66. Uh, 2 liters of 6 molar solution would contain 12 moles of solute independent of the identity of the solute. So how do we tell moles? If molarity equals that, then the number of moles equals this, right? So if we multiply, molarity is 6 molar times 2 liters is 12 moles. 12 moles of solute. Is that what it says? Yeah, 12 moles. So 1 is true. How about 2? For liquid solutions, volume of the solution is always greater than the sum of the volumes of the solute and solvent because of solvent-solute repulsion effects. No, you can't tell. It could be greater, it could be less, right? Regardless of what the reason is. It's not always greater. Could be less. Right, so 2 is false. 3. Osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. That's a good way to put it. Right? And our example was what? We had a container here of a saturated solution of something, and then we had a membrane here and a long tube, and inside here we had pure solvent. Oops, wrong way around. Nobody stopped me. Saturated solutions in here, and the pure solvents in here. Well, water. Let's just keep it simple. All right, so which way is the water going to move? In here. How long is it going to move? Till we get enough pressure built up here, between here and here, to stop it from moving. So that's the opposing pressure. That's the osmotic pressure is due to the height of this column that keeps the osmosis from occurring. That's why 3 is a true statement. So we had 2. B. B is the correct answer for 66. 67. For the set of ionic compounds, sodium nitrate, potassium nitrate, ammonium nitrate, choose the correct characterization of their solubilities in water from the response list. Okay, you can look at the solubility chart and say, okay, well, they're all nitrates. So you just take your nitrate, which is on the left-hand side, follow it across, say, sodium, potassium, ammonium. Are they soluble? Yep, all three of them. The general rule is that all nitrates are soluble, all ammonium compounds are soluble, all alkaline metal compounds are soluble. So they got three things going for them. They're all soluble. Okay. What's so funny? Oh, the conversation. Yeah. Maybe they ate too many pork rinds.
In their conversation back there in the hall.
Is it confidential? Yeah. You close the door? Okay. I don't know better than that. For the set of ionic compounds, lithium chloride, silver chloride, magnesium chloride, choose the correct characterization of their solubilities. All right. In this case, most chlorides are soluble. Lithium and magnesium chloride are soluble. Silver chloride is the exception. It is not soluble. So two of the three salts are soluble. That's B. Silver chloride is not. All right. Let's try who's next. Ooh, skipping a bunch. There we go. 80. Using the response list, characterize the osmotic pressure of a 0.80%, 0.80% magnesium chloride mass volume. With respect to the cells. Oh, okay. So if 0.9% sodium chloride is isotonic, and you've got 2 particles here, 3 particles here would take, let's just say roughly half of that would be 0.45 times 3, 0.45 times 3. This is just a rough estimate. 112 is 3, 1.35 would be compared to this one. We're trying to prorate this one to that one. This will be much, much greater than that. It would be hypertonic. Okay.